And it's really an open question in representation learning in general whether this type of robustness will give you a robustness in the real world on the naturally occurring images. Nonetheless, there are people who train the model. So we take some training subset, we manipulate the images in an adversarial way, and then we train the model. This is called adversarial training. And we see that the model can become a bit more robust on this type. So the performance drop between the blue lines and the red lines is reduced. But can somebody imagine what's happening when we try to train the model, so fine-tuning, let's say, the model to recognize adversarially manipulated images? So the robustness is reduced, but this happens at the cost of kind of forgetting the features and the representation that the model has learned. So the difference is reduced, but also the blue line, so the score on the initial distribution is significantly reduced. So you have this type of trade-off. And these are some of our own results on the lab with some other students. So we try to translate this idea of classifying images to out-of-distribution detection. So we had this baseline, the same you do on the exercise class, of taking the nearest neighbor similarity and using it as an OOD score. And we had this baseline of 86 for these two in and out distribution dataset. And then we take features. So this deer is an out-of-distribution image on the top left, as you can see. And then we take a random in-distribution image, which is this apple, and we bring the similarity of those two images, even though the class is completely different. We bring those similarities together. We basically maximize the similarity, and we, like the image on the center is basically manipulated, even though it's invisible to see on the human eye, so that it matches so that their features match. So for the model, this is in distribution, this is out distribution, but then when you do these small changes in the deer, by changing the pixels a bit, here you can see the Euclidean pixel-wise difference. So these are like some small changes, and the model is getting completely fooled, even though the human can't really. So these are like the adversarial robustness in terms of not just classification, also detection. So these CLIP ViT models are really full. And does somebody has any idea why this behavior is like kind of what are these squares indicate? Because we have this CLIP vision transformer. Yes?
The borders of the patches.
Can you repeat?
Is it the vision transformer, the patches? Like the
yes.
borders of the patches?
So this is the information, like the patch size. So for the patch size of 14 or by 14 or 16 by 16, we see there is also some sort of foreground. So the images that correspond to the deer, but also mainly that the borders around the patches are manipulated. Very nice. So then we added like a smoothness parameter to make these perturbations. So these are the gradients that will be propagated on the image, that will manipulate the image. We ask this we regularize this perturbation to not focus on the boundaries and on the boundaries of the path size, and this is like the end result. And the model can still be fooled. Like, do you remember what is the random guess in a binary classification problem? What is the random guess for our 50%? So these results are, this is even worse than random, and this is barely above chance level. Okay, so this is the summary. We have the pre-training dataset is the most contributing factor the training data distribution is the most important factor of these large-scale pre-trainings regarding CLIP, and that the choice of the pre-training dataset is task-dependent, so it influences for different it changes for different tasks. Regarding scaling laws, we need to scale all the three important parameters in tandem or simultaneously. So model in terms of parameters, data distribution in terms of how much data and how many samples the model sees. This is the equivalent of epoch-wise training to get consistent improvements and get this power law behavior. Then we saw that we can do extrapolation if we had if we want to train really large models that require maybe hundreds, maybe even millions of dollars, especially if you train on the cloud, which is much more expensive. And then we can do this extrapolation. We can apply this extrapolation of the linear line to predict how the model will perform if we land the experiment. And lastly, we saw that the model is not really robust to adversarial attacks, and from time to time you can have a hard time distinguish between different cats and eggs in the small game we tried. Any questions regarding CLIP? Okay. So now we want to see how much of these findings, and we try to follow up all the robustness analysis and all the literature of supervised pre-trained models. All right. So now we take a step back and we consider, because these CLIP models are 2 years old, so all these analysis of CLIP models and stuff, it's something that happened in the last 2 years since the first CLIP model and paper were released, this type of pre-training. So we take a step back and we are trying to slowly understand the literature, the corresponding literature in the supervised world. And we will start from identifying some key papers. So in 2018, so before the launch of the big vision transformers, there were this neuroscience group in somewhere in Europe that they found out, this is a very famous image, I will just briefly analyze. So here you can see the image, and here you can see with bold what the model predicts and with what probability, like the top 3 probabilities. So here the model is able to distinguish that this image is an elephant, which is the correct prediction. Here the model, I think this is a ResNet 50. The model is able to distinguish this image as a cat and also the correct breed of cat. And here when you overlay these 2 images, you can I say this? You combine the texture of the first image with the shape of the second image. So the whole analysis that we will talk so far is about these 2 components, let's say, texture and shape. We will analyze it. So first, I want to ask you another question. Can somebody imagine the texture of an image if it corresponds to high or low frequency features? Do you have any intuition if it corresponds to high or low frequencies?
Yes. Frequencies.
High? Okay. Raise your hand if you think the texture are high frequency features. Let's see. 1, 2, 3, 4, 5. Okay, you guessed correctly. So textures correspond more to high frequency features, while shape is believed to correspond to more low frequency features. There is this analysis to show that this ResNet and all the literature of 2018, all the existing models of 2018, which were primarily ResNets and in general convolutional neural network with batch normalization and everything. They are super sensitive to the texture of the image. And one very important part is that all these analysis was being conducted for ImageNet trained CNNs of 2018. So there are a lot of neuroscience-based studies, including humans on the loop, as an experimental subject, and there is a very strong indication that humans tend to focus on the shape of the image. What was the question?
Yeah, so when you say high frequency, it means that it comes out more often than the shape.
No, frequency. It means that in terms of signal processing. So the signal, you can imagine the signal if you do some maybe Fourier analysis or something. It has some spectrum of frequencies, and these. Let's say the high frequencies, you can imagine them as referring to really, let's say, really local information. So if you see like a very tiny path, you can identify some features there. So really localized information corresponds to, I don't want to make a mistake, high frequencies, which corresponds to texture. But texture is just one of the possible high frequency signals or features. Does it answer a bit?
Do you have more examples?
I will mostly talk about this shape versus texture. So shape, you can imagine that in order to get the shape of the object, you need to have access to the global information. You cannot infer the shape from a very tiny part. But in any case, I will try to find some more resources and send you about high and low frequency features with respect to images, because it's kind of two-dimensional, so it's a bit hard to get. So we know from neuroscience that humans tend to focus on shapes. And can somebody imagine why is that the case? Why humans tend to recognize scenes and objects based on shapes? Have we discussed? Yes?
Because maybe it has to, as the eyes have to work on dark or low light areas as well, and then you can more see the shape and the texture as well.
The shape and the texture, or just
more the shape than the texture?
More the shape than the texture. Okay. So you say about dark rooms. So what, like in terms of image processing, what would be, like given a room with light, what would be it's like a perturbation, right? In terms of formulating this as different lighting conditions, different angles, different noise levels, or it's just different perturbations. So we know experimentally and also based on our intuition that shape is kind of invariant to all those different perturbations, like what you say, if the room is dark, if there's like a rainy day, you can still see the building where you want to go, and all this. While texture is can change. All right, I hope this is clearly established. So this is like a real analysis. So the red, based on this bar plot, the red corresponds to human, and these are like 4 ResNets of 2018 at that time. So convolutional, convolutional neural networks. And they found out that the models are so bad at recognizing the objects that are kind of obvious to humans, apart from the grayscale. But you can see here the silhouette, which is basically the shape the model performs extremely bad compared to the human. And since we would like to make human-like or equivalent models, we want this idea of learning representations that are biased towards shape. So because it remains stable and kind of invariant, and while the other features can be easily distorted. Again, this analysis for image then. Okay, then let's see how does all these findings from 2018 can correlate a bit. How can we, what are like the vision transformers, like how much they can perform on this scale. So again, I just want to re-emphasize on the fundamental differences between the core module of convolutional algorithm, which is the convolution, where you have this inductive bias, as we say, of locality. So here you can see these reference pixels with the heavy weighted square, and then this is like the kernel size of 3 by 3. And then the output will be just the dot product of these two values, and then the kernel is shifted towards the grid. So for images, we have this two-dimensional grid. So based on the kernel size, the model is really limited to see local information, this locality, and then it's shifted throughout the grid, no matter how many dimensions we have. While on the other side, we have this visualization from visual transformers from the initial paper, that even very early layers of the network have access to all their surrounding, this kind of global information. Not exactly global, because we project everything into a sequence of patches, but still much wider range of information is available even from the early layers of the network. Any questions here? So this is another illustration, again quite high level. We perform these adversarial attacks, and we want to see how the model, how the gradients, how the model is updated based on the different. So we have a vision transformer and the ResNet, and we want to see how this model, how the image will change if it is so the same objective, maximizing the cross entropy instead of minimizing it. So and forcing the model to output a uniform distribution which has the maximum entropy. The first time we used a pre-trained vision, a supervised pre-trained vision transformer. The second time we used the ResNet, and you can already see this patch-based behavior similarly to the results we talked about before about CLIP. You see this, the boundaries are really easy to distinguish even from the human eye. So again, this is just an illustration that they process information in different ways. So it's only until 2021 where these different behaviors, so investigating the representations of existing ResNets, and again I'm emphasizing the fact that we're talking about mostly ResNets versus vision transformers, that these shape bias analysis were further investigated. So the red line corresponds to the human, how much humans are biased towards shape, which is something between 90 and 100%. And these are the scores for different models. They had some additional models, but I just removed them. So this is the ResNet. This one is a vision transformer that is also trying to mimic. It has like two tokens. The first is to classify the image, so the standard cross entropy, and the second is like the hard distillation from the ResNet model. So it follows the characteristics and the desired behaviors of the ResNet. While here it's just a vision transformer trained with cross entropy, and the bigger the model, even on the same dataset, the higher the safe bias. I don't have all the details about how this quantification from 0 to 1 is quantitatively realized, but the bottom line is to understand that even larger models are less biased towards texture, and at the same time that all the vision transformers are more safe biased than resonance. Any questions? So now we're investigating another part of the robustness, but not with respect to this analysis of texture shape, but now we're investigating the robustness against occlusions. So similar to what we said, that the distortions for the human eye can be to have like only part of the information, like heavy rain or snow or different noises. Here we mimic this behavior by randomly removing patches of the image, or randomly removing pixels in general. And the results I'm presenting here is when you take the image and do this block-wise masking, and then pass the information on the different resonance and vision transformers. So this is not the most fair comparison, because the transformer processes the information block-wise, so the transformer will not see these removed patches, while the CNN will still have to do this sliding. So this is a limitation of this grid-based. I mean when there is like a spatial grid. So the CNN still needs to process these empty masked patches. And here what they measure for different classes, they measure the correlation between having no masking versus 50% masking. So the ideal correlation would be 100%. And they found out that this bit large, which also has the highest safe bias, can also have like around 80% on average correlation. So even though we remove 50% of the information, we can still get the same outcome. This would be useful in applications, industrial applications, where you have like maybe some noisy sensor to get like your visual information, and you would need a model that would be very robust to this kind of noisily acquired data. Yes?
Is there some sort of, like, also cases where you don't want it to be exactly as good if you take some information out? Like, it might be reasonable to say that if you take out 50% of the information, the model is less confident, or it can't always identify. Like, sometimes that seems like it might be a good thing as well.
I'm not aware at this moment of any, like you're saying that instead of maybe some robustness is not really desirable. That's what the problem means.
I think with humans, sometimes you might not say that it's definitely the same image if you're missing 50%. Like there's something.
Yeah, but the baseline is that the human can still identify the class even if you mask 50%. So there is this kind of, let's say, trade-off. Okay, without being like 100% strict about it, you can imagine. Actually, I have some example. About that. I will keep this on the side. So next, they want to take this supervised pre-trained bits on ImageNet, take the features, and then train a linear layer or do some, let's say linear layer, some probing on some some out of domain, as they're called, classification datasets. So here we take the learned features from ImageNet and use this on highly varying dataset, like basically sifted distributions. So these are like images from aircrafts, I knew this dataset, but I kind of forgot. I think this is a dataset with different type of mushrooms, and this is like images from different photographers on nature. And you still see the same behavior. So let's ignore the blue bar plot, which is an ensemble, it's more complicated. But the ResNet versus the small, let's say, vision transformer has like is able to generalize. So these features are more transferable even to sifted distributions. So it's also true in the supervised case that these vision transformers are more transferable than ResNet, at least for ResNet 50. So here is what you told me about. So these are some results from our lab. So we are benchmarking. Let's focus on the bottom part. So we have different supervised models on ImageNet. So supervised pre-trained models on ImageNet. We don't modify the backbone. We keep the backbone. So we take the features of those models, and then we try to do clustering. So we have talked about clustering, but as image clustering, we need to assign one of the 1,000 labels to each sample in the dataset for ImageNet, and for Cypher 100, one of the 101. So we saw something quite interesting. So far I have only presented results about ResNets. So we were curious if the state-of-the-art convolutional networks would still be able to keep up with the advancements in vision, or if vision transformer were just the best architecture in general. And we find out that this ConvNext, which is an architecture which is convolutions just with different tricks, so they replace, for example, bus normalization with plane normalization, and they do some incremental changes that were discovered after the ResNet architecture was introduced in 2016. So it's like a convert that has all the different findings and intermediate advancements from 2016 to 2021, 22, more or less. And we found out that the features of this ConvNext, which is quite equivalent in terms of the number of parameters with a large vision transformer, so in the 100 million scale parameters. We take these features and we apply our own method, but the results are consistent with k-means. It's just that our method has like a larger improvement over k-means. It's the one you implemented, like a small version of what we did with scan and point-wise mutual information with the nearest neighbor. So we see that indeed the frozen features from the ConvNext are much better in the same training data distribution for clustering, even from the best vision transformer. However, when you transfer these features, so you take the features but you generate the features on Cypher 100, and then you try to do clustering here, you have a huge performance drop of ConvNext. So this is typically referred to in the literature as OD generalization. So how much the features generalize to unseen data distribution. So we imagine that ImageNet and Cypher have a different data distribution. Yes?
This unseen data distribution isn't data picked up from other sources, or is you purposely shifted or distort?
It's by definition is like another data distribution, and the model is never trained with Cypher images. The same thing we had here. So the model was never trained with this type of data. At least the backbone where we generate the features. So here we see a very different behavior. So even though the vision transformer has this amazing transferability to unseen data distribution, so it generalizes quite well, the ConvNext doesn't follow the same trend. And this is one really main finding that you can only see if you take the state-of-the-art convolutional neural network, because resonance still fall far below the vision transformers. So based on your question, like a couple of minutes ago, there might be applications where you would want to not generalize very well in unseen data distribution, and then you can, for example, use a different architecture. So far we talked about ImageNet pre-training, but nowadays we can, like the large corporations can go far beyond the 100 million parameter ViT large and the 1 million images. So the last thing we'll see is about scaling up the models and the datasets in the supervised case. So this is a first study from 2020-2021. So this ILS VRC is just ImageNet. So this is ImageNet accuracy, and this is the ImageNet adversarial, which is these images from the photosphere that I presented on the last lecture. So a very challenging ImageNet subset. And they again they tried different resonance and vision transformers, and all in all they found out that the ImageNet accuracy is a very good predictor of the robustness of the model, and that the vision transformers scale much better with model size. So as you scale up the parameters of the model for larger data sets, so these three bars correspond to so this is 1 million images, this is 14, maybe 20, I don't remember, like something in the scale between 15 and 20 million images, and this is like a proprietary data set from Google AI, which is 300 million images, and all are supervised pre-trained. And they found out that ViT models scale much better with respect to the model size and bigger data sets. And you can see here again the number of parameters. So this was more than 100, it's like 300 million parameters, small fix. Then a follow-up study of 2022 showed again this behavior in the log scale. So they even scaled even larger vision transformers. So from 600 million, they even scaled to this ViT Z small and Z big, which are on the scale of a billion parameter, 1 to 2 billion parameter scale vision transformers, with again minor changes on the architecture itself, pure self-attention, layer normalization, you know, all these parameters. We don't really touch the architecture itself. We just scale out the training schedule, the data set, and everything. And you still see this idea in terms of data set size, model size. Again, all the y-axis are the test error, and the fine-tuned error rate, which is 1 minus the accuracy. So here they scale it to 2 billion trainable parameters and 3 billion supervised images. And this is another recent work from the same team from Google AI, where they scaled up to 22 billion parameters as they are trying to catch up with the larger scale natural language transformer, which are, I think, more than, without being just as safe, is something like more than 100 billion parameter models. Maybe even more. How much?
GPT-4, I think it showed it.
Yes, I think it's more than the scale of 100 billion parameters, but I don't have the exact number. But the most important is to see that we just scale up these 4 parameters in the transformer architecture. So this is the D model parameter, so the dimension of the tokens. So each token has a specific dimension, D model in the transformer paper. This is like how many layers, the dimension of the MLP after the self-attention block, or the feed-forward neural network in the transformer paper, and the number of heads. And these 4 parameters gives us the final number of parameters. So this is like 2 billion, 21 billion. So almost 22 billion parameters. And and this was trained in 4 billion images with 3,000 labels. So this is like again appropriate. This is like they just scale up their data with some semi-automatic method every year, and they train even bigger models. So the bottom line is that you can have similar scaling up effects whether you train with CLIP and this contrastive language image objective, or as image caption, or even with supervised learning. It doesn't really make a difference as long as you have a very good training data distribution, a lot of compute, and scale up the models in parallel. So these are previous results from self-supervised learning from the previous weeks. And I think both are with linear probing. We don't fine-tune the whole model. And it's the first model that reaches almost 90% on ImageNet with linear probing. You know, the backbone is not fine-tuned. Yes. And another small, let's say, hint or like hidden trick is that they found a mapping. So when you have supervised learning, you cannot do this kind of zero-shot stuff as in CLIP. So they just found a mapping between a vast majority of the ImageNet labels on the big data set. So they have the big data set which has these 30,000 classes. And then ImageNet has only 1,000 classes. And then they map different classes from the big data set to the small data set. So this is a very cheap way to do this kind of zero shot. But you need to have a lot of, like a human needs to make this mapping. Yes, and we also have like this shape bias analysis. So shape of 1 is that the model is fully biased towards shape, and shape of 0 means that the model is totally biased towards texture. These are some old, smaller models, but again, everything is supervised, pre-trained here. And they found out that this 22 billion parameter model fine-tuned on ImageNet has the highest shape bias than all the previously recorded networks in the literature. A small problem is that they only considered the ViT-based CLIP. So I would be really curious to see how these larger and latest CLIP models play in this figure. But even with supervised training, we really learn or really shape bias features, very good at classifying ImageNet and everything. And they also see that you can classify, so what we talked about as OD generalization. So this is from the same work. This is another work that shows this linear trend again in the log scale between ImageNet and this ImageNet V2. So this robustness analysis. So this is all the supervised models on ImageNet, like 78 supervised models, independent of the architecture. And here, this is the 22, like with the red, it's the 22 billion parameter, largely pre-trained vision transformer. So this is the so-called zero-shot performance of these models that they train by label mapping. So the x-axis again ImageNet, and then this is the OOD out of distribution classification. So this is again classification, but on a sifted distribution from ImageNet. And they investigate how fine-tuning on ImageNet can also improve the so-called OOD generalization or OOD classification. Don't confuse it with OOD detection, it's like different tasks. So here we see this, the better we get on classifying ImageNet by fine-tuning these large models, we also get better at classifying all these naturally sifted distributions. So all in all, attention is the core mechanism that determines the robustness of the vision transformers. Even though these convnexts seem to be very good on the same data distribution, they are not so transferable as we have seen from some early experiments. So CNNs don't scale as good as the vision transformer, as the considered vision transformer in terms of scaling and modeling and dataset size. And they are less biased towards texture. And they also achieve very good robustness with respect to occlusions, also permutation, even though I didn't show these results. And most importantly, natural distribution shifts, which is something that people really care in real life applications. That's it for today. Any questions? Okay, thank you.